This is CPE 133. This is experiment 8, and what we're going to do here is design a 4-bit up-down multi-output counter, and it's going to be FSM based. It's going to be controlled by state machine. So objectives in this experiment is this is the first experiment dealing with state machines. It deals with state machines at a low level, and so you're supposed to understand how those work. Additionally, this is the first experiment. We'll be working with the clock divider module, which is provided, and we'll talk more about that later. So overall, what we're going to do is implement a 4-bit up-down counter, and that means whether a button is pressed or not, it's going to count up and down. Now, this counter has two outputs. It has a decimal output and has a Stone Age unary output, and a little bit more on that later. And what we're going to do is verify this, not with the simulator, but just visually. So there are many different ways to design a state machine. We're going to design this at kind of a medium-low level. Now, you could design this at a gate level using flip-flops and all that fancy stuff, which is what we used to do in the class, but we don't do that anymore. We've bumped up a level. So what you're responsible for is these 3 blocks right here. Now, the good thing is this is simply just a register. So the register is listed on Canvas. You don't need to do anything special for it. The main things you'll be doing in this experiment is designing next state decoder and an output decoder. And so this counter particularly has 2 count outputs. And one of the count outputs is a decimal value, which we're going to use the universal 7-segment display for, and the other output is a unary count. So 4-bit counter can count 0 through 15. The Basis 3 board has 16 LEDs on it, so they're going to fit on there. So you're required to drive those LEDs on the board, as well as make a decimal number appear on the development board. And not too big deal. What that's going to be is you're going to have 2 different outputs from this output decoder. Additionally, in this experiment, we're going to be running on the board, and we want to see it work properly. We need to slow down the board clock, and more on that in the next slide. And finally, we're going to visually test our design. No fancy test benches in this one, unless you really want to. So the clock divider module is a module that divides the system clock down to something slower. So it's clock division, starts high, ends up low. So there, on the board, on the development board, there is a 100 megahertz clock, which is, pretty fast. So what we need to do is divide that down into something that our eyes can see, because we want to be able to see this counter work on the board. And so this module here, it has an input clock frequency, which is the 100 megahertz frequency, and then it divides it down. We'll put a divide signal, and then it has a slower clock output. Remember, these are oscillators that look like this on the input, and something slower on the output. It's going to look like that. Now, the issue here is this has this other input here, this F clock only input, which means if you set this to a 1, it bypasses the clock divider, which is something that you can use for simulators. So that goes, you may not need to simulate this experiment, but later experiments you may need to get rid of the clock divider so you can properly test the thing. If there's a huge clock divider in your circuit, it's not going to, you're going to have problems testing it. So anyway, this when you instantiate this, you have to put a 0 or 1 into this F clock only input, which once again, 1 bypasses the clock division. This is a design that's fairly straightforward. I mean, the block, here's your block level diagram right there, roughly speaking. So it's almost like you don't really need to design this on paper first, but maybe you should. The issue is what you'll be doing is designing 2 decoders. One's next state decoder, the other one is the output decoder. You're going to use just a register module for the state registers, and make sure you look at the manual. There's some other notes in the manual that will be helpful. So this is kind of a multi-level design, yes or no, I don't know. The issue is you're going to instantiate your register. You can put your decoders on that level. You don't need to make your decoders as separate elements. You may want to, maybe for support future experiments, but you can have everything on the top level, meaning instantiate the registers, define the two decoders. It's up to you how you do this. And that is it.